All right, here we go, folks. Day 4 for us of rotation chapter. Okay, so sorry, what we've got here today is we've got Newton's second law of rotation. Now, just to preface the day, with Newton's second law, it is going to present some challenging equation, or a challenging equation for us that has a little bit of multiplicity to it. What I mean by that is we've got a couple different forms that we can start to work through with this one. Okay. Your quiz topics, angular measurements. Remember, that's like angular speed, angular acceleration, being able to convert those into linear stuff as well, always. Rotational kinematics, moment of inertia from yesterday, also today, obviously, and then Newton's second law for rotation. So you'll see some problems like that today, and then we'll go from there. All right. So, like I said, Newton's second law for rotation, it involves torque, moment of inertia, and angular acceleration. So when we see something like this, all right, if a rock were traveling straight, we could figure out Newton's second law pretty easily, right? Meaning that if we had this thing sliding, if we had this thing being thrown, we could do fun equals ma. So we could figure out how much unbalanced force that thing is actually traveling with in that direction. Now, the downfall for it is that is traveling in a straight line. So when we look at it, it's going the wrong direction. So if it's attached to a string, what will end up happening is we'll see it on a curved path. So instead of that one, we're actually going to get something like that. Now, because fun equals ma is for linear, we can't necessarily use that in a rotational path, meaning like this one, in an angular or curved path. All right. So because it's going to be in a curved path, we need to fix it. All right. So what that means is we can't use this linear form of Newton's second law. Now, you're not going to be asked to ever have to reproduce this, but I wanted to show you that there is a tangible reason why this came from where it did. All right. So you just don't have to blindly accept it. So first and foremost, I'm going to start with that acceleration up in that upper right corner there. Right. So I'm going to start with this. Now, as you remember from your linear conversions, acceleration can be converted to angular acceleration. The way that we do that is we have to use our alpha and the radius. Remember, alpha, that's our radians per second squared. Our radius is just this distance from the middle all the way out to here. Okay. And again, when we look at this, because if we say this thing is attached to a string and we're going to spin it, well, then it's going to be always at that radius right there for us. Okay. So we replace that in there. Now, when we look at this as well, now we've got our angular bit there, our rotational bit there. All right. So the next part that we're going to look at is this force here. All right. Force for us, usually when we go straight, that's fun. That's fine. We can calculate that. Right. But if we have a twisting or if we have a turning, remember back to last chapter when we talked about torque. Right. This thing is going to curve around that central pivot point. Remember Brian on a beam, right? We set up a pivot point, and now we had this upward torque, right? Cantilevers, seesaws, all of it was the same stuff for us. We were twisting that thing around and trying to get that thing to move around a central pivot point, okay? So because of that, our force is just torque divided by the radius, right? Again, because we're talking about a circular object, this is our distance. This is our radial arm, so to speak, or our radial distance. So because of that, we can put our radius in right down there, right? And obviously torque equals force times distance, but I just rearranged it so that I could plug this straight in, all right? So when we get that, that looks pretty dang messy. You know what I'm saying? So if I put in my torque over divided by my radius here, that gets kind of gross. So then I've just multiplied both sides by radius, okay? So by multiplying both sides by radius, that helps to get it so that it looks a little bit better, right? So there's my torque, and I just moved that radius that we were using right over to there, all right? So once we've got this cleaned up, well, we still have a mass variable. We could use the mass. Don't get me wrong. If we wanted to find the torque around it, we could use the mass. But as you saw at the beginning of the lecture, right, this is about torque, angular acceleration, and then moment of inertia. All right. So moment of inertia, right? This mass is a contributing factor in that. All right. So remember that a mass doesn't want to move. That's what its inertia is. Remember? That's Newton's first law. Object at rest stays at rest. If you think about, you know, if I use my calculator and I just lay it down on the desk on my table here, right? It's going to stay there until an outside force acts upon it. Just like this rock. That rock does not want to move until we actually start to swing it and force it. So that's its resistance to movement, which is I, big I, a rotational, or I'm sorry, some people are moving or want to make it called rotational inertia. I kind of like it. But our moment of inertia is going to be mr squared, if you remember that right. Okay? So what we have to do then is we have to rearrange this a little bit, right? So what ends up taking place is we divide r squared over here, and we put in I over r squared. Let me show you that since I didn't do that on the actual dealio. So this will be I over r squared. So what ends up happening is that we divide all of this by r squared. Well, those two cancel out, leaving me with an I here. So then what we see is, here is our second law for rotation. Torque equals the moment of inertia times the acceleration, angular acceleration. All right. And I got a couple key pieces over here for you. All right. Remember, torque is force times distance. That distance, we could sub that out for a radius here, right? Like this thing here, if we wanted to calculate that. That works. All right. And then I equals mr squared. Now, remember, this is going to be dependent on the object that we're looking at. If it's a hoop and we're spinning a hoop around in a circle, that works. If it's usually anything else, I'll tell you. All right. Like I have in the example today, I'll make sure I verify that for you so that you can see that. Okay. So that's how we get the formula to be able to say, okay, Newton's second law is this, but for rotation, we need it to be this. The torque is about that twist, that forcing twist. Moment of inertia is getting that mass to actually move, right? And then alpha, that's just our acceleration. So that's where we kind of get our fun equals mod stuff. All right, so here we go. So front little video was a preview or appetizer, if you so choose, towards this problem, okay? We got a revolving door is made up of 4 panels of glass connected to a central hub. The length of each panel is 1 meter. The mass of each panel is 40 kilograms, all right? So for part A, we want to determine the moment of inertia for the entire structure, meaning that we're going to consider each panel to be a long rod. Now, if it's something out of the ordinary, like if it's a hoop or a tire, you get that. That's I equal mr squared, right? If it's a solid disc, that's 1/2 mr squared. Those are ones that I showed you a while ago. This one, I don't expect you to memorize. If we start to use it more and more and more, I'll likely tell you to write it down. But at this point in time, please do not worry about it yet. Okay. So, and then part 2, since Buddy the Elf, you can see that one. Part 3, part 4, we'll get to that one. Let's just work part 1 first. Okay, so part A. What we want to do here in part A is we want to determine the moment of inertia. All right, because we're considering this like a long rod rotating around its end, basically what that means is that I'm rotating this like this. I'm considering that that's my long rod on my ruler, okay? So I take my radius, which is the length of the door, of that door panel rod, right? And then the mass of it is right there, okay? So we plug that in to our equation since we are using the moment of inertia based on kind of it being rotating around the end. And we end up finding that this is 13.3 kilogram meter squared. That's for one of our panels. Now, here's the crux of it. We need the whole thing. So in order to get the whole thing, because this is only one panel, we have to actually take it times 4 for all of the panels. We're going to say that all of those panels are consistent with that one that we had, and all of them are going to have the same consistency throughout, the same mass relationship, the same length, the same distribution of mass, all of that stuff, okay? So what we end up seeing is our total moment of inertia, or rotational inertia, if you want to call it that, is 53.3 kilogram meter squared, all right? So part B then. It says, since Buddy the Elf loves revolving doors so much, you create a contest within one. You push with a force of 150 newtons at 70 centimeters from the center hub. Okay, so that gives us a radius there, right? Well, Buddy pushes the exact same direction with a force of 120 newtons at 90 centimeters from the center hub. What is the net torque? Now, this is something very similar to, seesaws, very similar to cantilevers, very similar to Brian on a beam, in that we're just looking at the torque being pushed in multiple directions, all right? So what I did over here was I put in my moment of inertia, which doesn't help us on this problem, but then I put in our force and distance and Buddy's force and distance, all right? Again, I'm trading out this distance here for a radius. In reality, it's the same thing. It's just how far away from the center are we, okay, that we're applying that force, all right? So then what we say is my torque is going to be 105 Newton meters. Buddy's torque is 108 Newton meters. Now, when you're looking at this, this is what I meant by you're pushing the same direction. If this is our spinning door here, we are right here pushing that way. Buddy is right there pushing that way. Who should win? Buddy should, right? Now, because they're both going technically that way, right? If I were to rotate this around, Buddy is actually pushing against me in this fashion. So he could be the torque up, I could be the torque down, so to speak, right? So what we end up seeing is our net torque is going to be 3 Newton meters, right? Hopefully that makes sense for you. Hopefully that isn't too tricky. Okay? So then it says, which way does the door spin? Well, it's going to spin the direction that Buddy pushes it, right? Because he's got more. And then what is the angular acceleration? Well, in this case, we know our moment of inertia, rotational inertia. We know our net torque. So we're just going to plug those in for our spots there, solving for our angular acceleration. So 3 divided by 53.3 gives us an angular acceleration of 0.056 radians per second squared. And again, that's going to move in the direction that Buddy is going to push on the door. All right. So that's kind of the second law for rotation question. Then here's an add-on just to make sure that you're getting good with rotational kinematics. Part D. How much time would it take to have Buddy make 1 revolution, assuming it starts from rest? From rest is a key term again. So I've got my moment of inertia yet. It's not going to help me for this one. I've got my torque net. Not going to help me for this one. I've got my angular. That's good. Now, I do have this 1 rotation, but I can't use rotations. So I have to use radians. So I just took the 1 rotation times the 2 pi. Okay. Then in looking at this, what I did was I tried to look through and I tried to see which one of these equations is going to be the best for me, right? If I know this, know my acceleration, and know that it starts at rest. Don't have a time, don't have a time, don't have a time, don't have a time. So that's why I chose this one here, okay? Plug in my values. There's my number of radians that it rotated. There's my initial velocity. There's the alpha that I just calculated in the previous question. So I take 2 pi divided by 0.0281, get 223, square root that for both of those. My time it should take for this to make 1 complete rotation should be 14.9 seconds, right? I know it's pretty involved. I know it's pretty intense, but hopefully through working some of the practice questions and also doing some of the homework stuff, that'll make a little bit more sense for you. Okay? Let me know if you got questions. Bye-bye.